Hi, this is our 2031 project demo. Our group is Tyler Boyer, David Casanova, Grant Elder, Matthew Liang, and Spencer Borg, and we are the Epic team. So, the problem that we were trying to solve is that the current LED peripheral on the SCOMP only supports being on and off, and our task was basically to expand upon this functionality. The requirements for this were to use these unused addresses on the SCOMP and to avoid modifying the capabilities already on the SCOMP. And the solution itself has to be a hardware solution and not a software solution because this is a hardware class. So the peripheral we wanted to make was basically a variable brightness feature for the SCOMP. Um, and this would have like a wide range of uses. But the way we used it in our project was we made the Towers of Hanoi game, and basically three LEDs would be one tower, and we'd had three towers, and then the brightness of the disc would be the size of the disc. And originally we were gonna have it so the three buttons represented the tower and you can actually solve it yourself, but due to time constraints we just made the Towers of Hanoi so that it's automatically solving itself, and that's what you'll see later in the demo.
To make the peripheral easy to work with for the programmer, we developed a simple API that goes like this. At the address 0x20, the I/O address, the I/O controller will enable the LED peripheral, and it will take in data from the accumulator. That data will be parsed into a section of 10 bits, 0 to 9, and 4 bits, 12 to 15. 0 through 9 is the LED bit mask. That is essentially what toggles LEDs to be changed or to not be changed when you change the brightness data. Um, basically what this means is that if an LED is not toggled, if you change its brightness data, then the brightness data that had previously been set to will be the brightness data it continues to use. Now, if you have that LED toggled, or that brightness data that you change the LED to, the LED will change to that brightness. So it essentially allows the programmer to set LEDs at one certain state or to change them to different states. The register selection bits is what allows for going from toggling functionality to the actual brightness changing functionality by basically having four selected bits and four states. In that sense, 0, 1, 2, and 3. 0 is toggling 1, 2, and 3 of brightness manipulation, which is what we're talking about now. As you see, the peripheral reads the selection bits and determines data to change. And these three different states, determined by the register selection bits, the bits 0 through 11 represent LED brightness data. And so that allows for four LEDs to have 3 bits of brightness data each, which allows for each LED to have 8 brightness states. And by doing this, we allow for both individualized LED brightness manipulation, as each LED can have its own brightness separate from other LEDs, and it also allows for the toggling and detoggling of LEDs. It allows for basically setting LEDs at one certain state or allowing them to be manipulated as soon as you call an out command on the address for the LED peripheral. Now, here's an example of SCOMP code interacting with our peripheral. Here you can see two accumulator values, the toggle values and the LED values. You can see that they both have their own four selected bits. The toggle has four zeros, which means it's a toggle state, and the brightness value has two zeros and two ones, which means that it is selecting one of the brightness control states. And bits 9 through 6 and the toggle are enabled. That means that LEDs 9 through 6 will be the only ones that can have brightness changed physically. All the brightness data can be manipulated, but the only ones that will actually show this change will be bits LEDs 9 through 6. And then the brightness data, it basically has values set for the LEDs 9 through 6, so each of them will have a different brightness value. And then if you look at the code right below it, you can see how those values are inputted into the BLED, which is simply address OX20, and then by inputting it into that address, the data will come out of the peripheral into the LEDs. Some key design elements to take note of about our API is that it separates brightness register per LED, and change takes effect immediately if the LED is enabled. If the LED is not enabled or toggled, then that change will only happen once the LED is toggled again. And then we also, due to the register-based architecture, this program will also support scalability. Now to show a little bit of the technical side of our peripheral, here is the schematic that shows the entire processor and all the different peripherals that connect to it that is being loaded to the FPGA. You can see that the I/O decoder connects to the LED controller, which has the LED enable and I/O data and everything. And a big thing to note is it has a clock. The clock is what allows for duty cycle changes, which is what enables the brightness manipulation. And then, as you can see, our data that takes in the accumulator value, which is for used for parsing, which is seen in the API. Now here's the actual VHDL of the program. You can see a bunch of different signals. Let's look real quick. The LED toggling and brightness tuning is here. This process here is what actually parses the data. It allows for the toggling state or the three different states of LED brightness control that you can choose based on the four register bits. You can see those register, or four selection bits, I should say. You can see those selection bits here. Brightness control mechanism, which uses the clock. Essentially, each clock cycle, each LED's brightness value is calculated based on what was inputted into this register. And then once each value is calculated, a mod operation is called, which will basically determine the brightness of each LED on each clock cycle. By determining each LED's brightness on each clock cycle, we are basically able to have individualized LED brightness control. And at the end, you can see the L data. The data is inputted into the LEDs each time because the LEDs themselves are separate from the peripheral. And so each clock cycle, we basically have to use the peripheral to determine which LEDs are going to be enabled and which LEDs are not going to be enabled. And that is what allows for brightness control.
I will be presenting our technical demo, which showcases our SCOMP assembly code that utilizes our brightness LED peripheral on the GE10 board. For that, we have an animation of the solving of the Towers of Hanoi problem. So our looping cycle has three towers, which are three groups of three LEDs. We start off with three disks, where disk size is represented by brightness level. Essentially, the brighter the disk on the GE10 board, the brighter the physical disk would be in the actual physical Towers of Hanoi problem. And we've utilized the timer peripheral to play the animation on a more human timescale so we can actually see it play out as shown here. So you can see the LEDs in different brightness levels moving across the board. And this is just an example of a use case that could not be used with the traditional LED peripheral. You could perhaps do some sort of Towers of Hanoi representation in binary or something like that, but it would not be nearly as readable or understandable as this is with our brightness implementation. So that's just one example use case.
So after looking at the demo that we developed that is on Towers of Hanoi, here are some other use cases for the peripheral that would be useful for future programs. You could potentially create various patterns for string lights using a peripheral by changing the brightness and having multiple LEDs next to each other of different brightness and gradually like changing all the LEDs, basically creating a pattern through the string. You could also have a loading bar where you essentially set each LED at the start to a very low brightness and then gradually raise them up and keep going from each subsequent LED in a line of LEDs, and then eventually you have all the LEDs at full brightness. You've basically created a loading bar. You could also have centralized brightness control of many different rooms. If you have LEDs in different rooms, and you connect them all to this peripheral, then the peripheral will essentially communicate with the LEDs in each room based on what the user inputs in their program, and it can allow for different rooms to have different brightness, and could also allow for different rooms to have the same brightness if you want to group them up, or you could have multiple LEDs in one room, have them all the same brightness. There's all sorts of possibilities there. You could also have gradual brightness shifting, which goes back to the loading bar, where you essentially have each LED gradually increasing or decreasing in brightness. So you could have, like, for example, you can make the loading bar, you can even make like an alarm system, where essentially you have like an LED that gradually gets bright, and then dark, and then bright and dark. There's all sorts of possibilities that future programs can use our peripheral to achieve. And so, in conclusion, our peripheral supports individualized LED brightness manipulation, and it's designed with scalability in mind, and also allows for toggling and brightness control capabilities, which gives the programmer so much opportunity to develop amazing things with the LEDs in an easy fashion by interacting with our API, by essentially state locking certain LEDs, allowing other LEDs to have brightness control whenever. And through this project, we have also tested and demoed our peripheral through a Towers of Hanoi animation, showing just a small sliver of the possibilities that the programmer can use our peripheral to achieve. Now, thank you for listening to our demo.